On March 17th, 2026, over Ohio, a rock from space exploded with a force of 250 tons of TNT. Zero warning came. Not one telescope had seen it approaching. And this event stood far from alone. Fireballs have illuminated the skies, stretching from Louisiana Strait through to Germany, where fragments actually struck a house. All of that unfolded inside a single month. Some researchers suspect Earth could be crossing a debris trail left behind by 3 Atlas, an interstellar visitor arriving from an entirely different star system, which carries truly terrifying implications. And right now, a coronal mass ejection heads our way, arriving precisely when the equinox lowers Earth's magnetic defenses to their weakest point all year. Coincidence or convergence? Stick with me until the very end, because what unfolds above us at this moment is either extraordinarily bad luck or something far more unsettling. If this already has you hooked, subscribe to the Skylab, since the sky is not finished with us yet. And we plan to cover every fireball, every solar storm, and every single moment the universe reminds us exactly how small and exposed we truly are. Drop a comment below sharing your honest take. Is March 2026 simply a cosmic coincidence? Or is something out there trying to grab our attention? Now let's dive in, because the story only grows stranger from here. Part 1. The 8:57 a.m. impact. Nobody watched. Nobody saw it approaching. Not NASA, not the Air Force, not a single telescope anywhere on the planet. And yet at 8:57 a.m. on March 17th, 2026, something arrived anyway. It was a Tuesday morning, the kind that begins exactly like every other. Commuters sipped bad coffee. Kids waited at bus stops. A woman in Cleveland scraped frost from her windshield while mentally rehearsing a meeting she really didn't want to attend. The sky above northern Ohio stayed clear. Temperatures sat in the low 30s. Nothing unusual appeared at all. Then the sky cracked open. Witnesses described it almost word for word across 10 different states. A flash. Not like lightning. Not like anything seen before. Brighter than the sun itself for just a fraction of a second. Like someone pressed a welding arc against the sky and then yanked it away. A truck driver on Interstate 77 thought he had gone blind. A woman in Pittsburgh glanced up from her phone and genuinely believed for about 3 seconds that the world was ending. She wasn't entirely wrong to wonder. What they watched was a piece of rock roughly 6 feet across, about the size of a small car, entering Earth's atmosphere at roughly 45,000 miles per hour. Let that sink in for a second. 45,000 miles per hour. At that speed, you could travel from New York to Los Angeles in about 14 seconds. The object came in over Lake Erie at around 50 miles altitude, screaming southward, and it glowed. Not because it burned like a candle, but because the air ahead of it compressed so violently that it turned into plasma. The rock itself wasn't burning. The sky around it was. It traveled approximately 34 miles before it could hold together no longer. Above Valley City, Ohio, a small community just north of Medina County, the object fragmented. It didn't break apart quietly. It exploded. The NASA Meteoroid Environments Office later estimated the energy release at around 250 tons of TNT. The Center for Near-Earth Object Studies placed the figure slightly higher, closer to 0.37 kilotons. Either way you looked at an explosion larger than some small military warheads detonating several miles above a neighborhood on an ordinary Tuesday morning. The shock wave reached the ground roughly 1 to 2 minutes after the flash, which confused many people. They saw the light, returned to their coffee, and then their house shook. Windows rattled across suburbs in northeastern Ohio. Car alarms triggered. A woman in Medina said her kitchen cabinet swung open like she stood on a ship in rough water. 9/11 dispatch centers across Ohio, Pennsylvania, New York, Maryland, Virginia, and Washington, D.C. flooded within minutes. People reported explosions, earthquakes, gas line ruptures, even a plane crash. Nobody knew what had happened because nothing like this had ever happened to them before. Eyewitness reports eventually mapped the spread across 10 states and into Ontario, Canada. The American Meteor Society logged hundreds of observations inside the first hour. Social media lit up with doorbell camera footage, dash cam clips, and security feeds, all showing that same impossible flash and that same silent skyfire racing faster than thought across the morning. Confirmation arrived quickly from instruments that never lie. NOAA's GOES 19 satellite, the one carrying a geostationary lightning mapper built to track electrical discharges, detected the fireball's plasma trail. The instrument registered it as lightning because, in a sense, it was a massive electrical discharge event triggered by superheated atmospheric plasma. Seismic instruments across the region picked up the shock wave as it coupled with the ground. Not an earthquake exactly, but something that registered like one. The physics doesn't care what label you give it. Energy is energy. Meteorite fragments are believed to have fallen across Medina County, making this potentially the first confirmed meteorite fall inside the United States in 2026. Hunters already search fields and backyards with maps and metal detectors for pieces of whatever arrived that morning. Here is the part that should stay with you. Not the explosion itself, not the shaking buildings, not the flooded 911 lines. Those moments feel dramatic. This is something else entirely. The object that exploded over Ohio on March 17th was detected for the very first time when it struck our atmosphere. There was no warning, no 48-hour alert, no heads up that something approached. No telescope anywhere on Earth had ever spotted it. No radar had tracked its path. It came from space, traveled whatever distance it traveled, and arrived without a single human being knowing it existed until it announced itself in fire and sound above a county in northern Ohio. We didn't miss it because we looked the wrong direction. We didn't miss it because of a malfunction, a budget cut, or someone falling asleep at a monitor. We missed it because the systems we built were never designed to see something that small. And here's the thing about that. It raises a question nobody in the news cycle seemed interested in asking. If this one stayed undetectable, how many others travel out there right now tonight on their way here that we also cannot see? That is not a rhetorical scare tactic. That is simply the next logical question. And the answer, as it turns out, feels considerably more unsettling than the explosion itself. Because here is what makes this story genuinely different from your standard space rockfalls. Scientists say, don't worry, news cycle. This wasn't a one-off, not even close. And what happened in the week surrounding March 17th is the part that should make you sit up straighter. Part 2, the physics of a small explosion that shook a city. 250 tons of TNT sounds enormous. And it is, but most people hold no real frame of reference for what that means when it detonates above your head instead of on the ground. Understanding the physics here separates dismissing this as a curiosity from grasping why the scientific community takes even small impact seriously. Start with the basics. TNT serves as the standard unit scientists use to express explosive energy because it stays familiar and consistent. A large car bomb, the kind used in major terror attacks, typically releases energy equal to a few hundred pounds of TNT. A World War II-era bomb, dropped by a heavy aircraft, released energy in the range of half a ton to 2 tons of TNT. The Ohio fireball released energy equal to 250 tons from a rock the size of a small car. That is not a geological curiosity. That is a significant energy event by any military or engineering standard. But here is where the physics turns genuinely interesting. Most of that energy never reached the ground in concentrated form. The reason buildings shook instead of collapsing, the reason nobody died, comes down to altitude, geometry, and the remarkable energy-dispersing properties of the atmosphere. The object exploded at an altitude of roughly 45 kilometers, give or take. That sits high, well above the weather layer, well into the stratosphere. When a rocky body traveling at hypersonic speed hits thicker and thicker layers of air, the pressure ahead of it builds faster than the material can structurally handle. The rock doesn't melt from friction the way people imagine. It gets crushed. The ram pressure, the sheer force of air that cannot get out of the way fast enough, builds up until the stress exceeds the object's internal strength, and then it disintegrates explosively. The technical term is air burst, and it behaves less like a bomb and more like a pressure wave generator. All that energy, the kinetic energy the rock spent years or centuries accumulating as it traveled through space, converts almost instantaneously into heat, light, and a rapidly expanding shock wave. The light arrives at the speed of light, obviously, which is why people saw the flash first and stood there confused for 60 to 120 seconds before the boom caught up. Sound travels at about 760 miles per hour at sea level. The shock wave had miles of distance to cover. It took its time. When that overpressure wave finally arrived at ground level, it had already spread across an enormous spherical volume of atmosphere. The energy diluted by the geometry of the explosion, spreading outward in all directions simultaneously. What reached a house in Medina was a tiny fraction of the total energy, but was still enough to physically push on every surface of that house at once. Windows rattled because the glass had nowhere to flex. Cabinets swung open because their hinges weren't designed to handle brief, uniform pressure from all directions simultaneously. The shaking felt like an earthquake because the mechanism is surprisingly similar, a sudden transfer of energy into the built environment. Daylight fireballs are genuinely rare, and this is worth pausing on. For a fireball to stay visible in broad daylight against the full brightness of a sunlit sky, it has to be extraordinarily energetic. Your eye already processes maximum ambient light. For something to appear brighter than the sky itself during the day, it needs to generate more light than the sun is delivering to that patch of atmosphere. Only the most energetic atmospheric entries qualify. The Ohio event absolutely qualified. The plasma trail surrounding the fragmenting object was hot enough and bright enough to outshine a clear morning sky, which is why witnesses across 10 states and a Canadian province could see it clearly. That plasma trail is also why the GOES 19 satellites lightning mapper detected it. The instrument was designed to detect the optical signature of lightning, rapid, intense light flashes from atmospheric electrical discharges. A superheated plasma channel surrounding a hypersonic projectile produces an almost identical optical signature. The satellite didn't know it watched a meteor. It simply knew it watched something that looked exactly like a very unusual lightning event. Instruments, like most of us, can only report what they're built to recognize. The seismic detection deserves its own moment of appreciation. Seismometers are buried in the ground specifically to detect vibrations traveling through rock and soil. They're not supposed to care about the atmosphere. But when a large shock wave hits the ground, it transfers energy downward, a process called atmospheric to seismic coupling. The instruments pick it up as a surface wave. No one at those seismic stations initially knew what they saw. They just knew something had transferred a significant amount of energy into the ground across a broad area, which is unusual. For perspective, the Chelyabinsk meteor over Russia in February 2013 released energy equivalent to roughly 440 kilotons of TNT, about 30 times the power of the bomb dropped on Hiroshima. It injured over 1,500 people, mostly from broken glass caused by the shock wave. It damaged thousands of buildings, and it too was completely undetected before entry. The Ohio event was dramatically smaller, but it came from the same category of threat. Same detection gap, same zero warning arrival, just a smaller package. The reason nobody was injured in Ohio comes down to a combination of lucky altitude, lucky trajectory angle, and the fortunate fact that the object was dense enough to fragment high rather than low. A shallower entry angle, a slightly denser object, a lower fragmentation point, and you look at a very different outcome in a region with over 1 million people inside the potential impact radius. So the next time someone says it was only 250 tons of TNT, remember that the word only does a lot of work in that sentence. And then ask yourself the question this naturally leads to. If this stayed small enough to remain completely invisible to every detection system on Earth, what exactly does a slightly larger version look like? Part 3. The detection gap that shouldn't exist. Most people assume in a vague and comforting way that NASA has this handled, that somewhere in a room full of screens, serious people, and headsets track every rock in the solar system. And if something headed our way, we would know. This assumption is understandable. It is also, for a specific and deeply inconvenient size range of objects, completely wrong. Here is how asteroid detection actually works. The primary tools are ground-based survey telescopes, networks like Catalina Sky Survey, Pan-STARRS, and Atlas, that scan large sections of the sky night after night, looking for moving points of light against the fixed background of stars. When they find something moving, they calculate its orbit. If the orbit looks like it might intersect with Earth at some point in the next 100 years or so, it gets flagged, tracked, and added to databases maintained by organizations like NASA Center for Near-Earth Object Studies, or CNEOS. This system works remarkably well for objects above a certain size. Anything over roughly 140 meters, the threshold for what's classified as a potentially hazardous asteroid, has a reasonably good chance of being spotted years or even decades before any potential impact. The larger the object, the easier it is to find. Kilometer-scale objects that could cause regional or global catastrophe. Scientists believe they've cataloged more than 90% of those. That is actually impressive work. But here is the gap. Objects in the 1 to 20 meter range, small enough to fall through the cracks of survey sensitivity, large enough to cause significant local damage, are effectively invisible until they hit us. The Ohio rock was approximately 1.8 meters across, weighing around 7 tons. For context, that is the mass of a fully loaded pickup truck traveling at 45,000 miles per hour. And no survey telescope on Earth detected it, because at that size, it is simply too small and too dark to register against the noise of the sky until it is already inside our atmosphere. There are several compounding reasons for this. First, small objects reflect very little light. A dark carbon-rich rock a couple of meters across produces an optical signal so faint that it is essentially invisible to current survey technology until it gets extremely close to Earth. And extremely close often means already entering the atmosphere. Second, many of these objects approach from the direction of the sun. Survey telescopes can only scan the nighttime sky. Anything coming from the sunward direction stays hidden in solar glare until it is too late. The Ohio object almost certainly approached from a sunward trajectory, which matches the morning arrival time. Third, these objects move fast. Even if a telescope happened to catch the light from such an object, the time between initial detection and atmospheric entry could be hours, not days or weeks. The frequency of these events is the part that most people find surprising. Objects roughly the size of a car enter Earth's atmosphere every few months. Smaller objects, basketball-sized, refrigerator-sized, arrive far more frequently, possibly daily, most of them disintegrating harmlessly far above populated areas or over oceans. The vast majority go completely unobserved. We know this not from direct detection, but from statistical modeling and from the occasional flash picked up by government sensors or satellite instruments that weren't specifically designed for the job. Chelyabinsk, the biggest atmospheric impact event in modern recorded history, was a 20-meter object. It approached from the sunward direction. Not a single survey telescope saw it coming. Scientists confirmed its existence only after it arrived. For comparison, the Ohio object was roughly 1/3 the size of Chelyabinsk. If Chelyabinsk stayed invisible, everything smaller than it is essentially guaranteed to stay invisible too. The term some researchers use for this problem is planetary defense blind spot. We've optimized our detection systems for the objects that could end civilization, and we've done reasonably well at that. But we've left a wide open window for objects in the range that can level a city, damage a region, or cause casualties in the thousands. That is not a political failing or a funding scandal. It is an engineering reality given the current state of technology. The Vera Rubin Observatory, now coming online in Chile, promises a significant improvement. Its camera, the largest digital camera ever built, can survey the entire visible sky every few nights with extraordinary sensitivity. It will detect millions of new asteroids. But even Vera Rubin struggles with the small, fast, sunward-approaching objects that pose the most sudden threat. The cadence problem, how often the sky is rescanned, means an object could still arrive between observation windows without triggering any alert. Here is the psychological layer underneath all of this. Humans are very good at fearing things they can see. We fear snakes, spiders, aggressive drivers, stormy weather. We are considerably worse at fearing threats that exist statistically, invisibly, and at unpredictable intervals. The asteroid threat lives in that second category. It doesn't announce itself. It doesn't build gradually. It arrives, or it doesn't on a timeline entirely indifferent to our awareness of it. What changed on March 17th wasn't the threat. The threat has always been there. What changed is that this time we received a very loud reminder that the blind spot is real and that it is not going away anytime soon. But here's the thing that will keep you up at night if you think about it too long. What if this particular blind spot isn't just about the limits of our technology? What if in March of 2026 something genuinely unusual is happening in the space around Earth? Because when you look at everything else occurring in the sky, that same month, a single detection failure starts to look less like a background condition and more like a symptom of something bigger. Part 4. This was not a one-off. Before March 17th, before the Ohio explosion and the flooded 911 lines and the meteorite hunters combing Medina County, the month had already turned strange. Not in a vague, hard-to-pin-down way. In a very specific, well-documented, scientifically observable way that wasn't getting nearly the attention it deserved. The first notable event arrived in mid-February. Another fireball sighting over Ohio that generated significant eyewitness reports but didn't reach mainstream awareness. Then in early March, things began to accelerate. On March 3rd and 4th, separate fireball events were reported over Louisiana and the Pacific Northwest within roughly 24 hours of each other. Two major sightings at different ends of the continent inside a single day. Unusual but not impossible. March 8th is where things got harder to wave away. The European Space Agency confirmed a significant fireball event visible across multiple countries simultaneously. Germany, France, and several neighboring nations reported the same streak of light on the same night. This wasn't a regional sighting. This was a continental-scale event observed by millions of people across an entire continent who had no idea they all watched the same thing. The ESA's confirmation came prompt and detailed. This was a real, well-documented, energetic atmospheric entry over Europe. And here's the part that makes it matter more than the headline suggests. Fragments struck a house in the Koblenz-Gulls area of Germany. An actual meteorite fall. Rocks from space landing on a residential structure. The homeowner reportedly found fragments on their roof and in their garden. March 9th brought another fireball event over the northeastern United States. The third significant North American sighting in less than 2 weeks. March 13th produced reports from Virginia. March 15th brought another Ohio event. And then on March 17th came the main event. The 7-ton object exploding over Valley City with a force of 250 tons of TNT. Lay those dates out in sequence and read them again. Mid-February, March 3rd, March 4th, March 8th, March 9th, March 13th, March 15th, March 17th. That is not a random scattering of events across a month. That is a cluster. Multiple events, multiple continents, multiple confirmed sonic booms inside a rolling window of roughly 3 weeks. To understand why this is unusual, you need to understand what a fireball actually is. The technical definition requires the object to reach a peak brightness greater than the planet Venus, which, when Venus is at its brightest, appears as an extremely obvious object in the night sky, brighter than everything except the moon and the sun. Most meteors, the ordinary shooting stars you see during a clear night, are nowhere near that bright. They are dust grain to sand grain-sized particles burning up dozens of miles above you. Fireballs are different. They are caused by larger, denser objects, rocks, not dust, and they represent a meaningful energy input into the atmosphere. The distinction between fireballs and bolides matters here too. A fireball is a very bright meteor. A bolide is a fireball that explodes, that undergoes a visible fragmentation event, often with a sonic boom. The Ohio event was a bolide. The Germany event produced recovered fragments, which means it was energetic enough to drive material through the atmosphere intact. These are not everyday occurrences. In 2025, there are only a handful of confirmed meteorite-producing falls globally for the entire year. The first 3 months of 2026 appear to run substantially ahead of that pace. And when you look at 2025's record and compare it to what March 2026 alone seems to deliver, the statistical contrast is jarring. Multiple researchers inside the small body astronomy community began noting the clustering publicly in the days following the March 17th event. The language stayed careful. Scientists are professionally trained to resist dramatic conclusions, but the observation itself was impossible to suppress. This month is running abnormally high for significant fireball events across multiple continents inside a compressed time window. So here's the question that naturally emerges, the one that some researchers are now whispering rather than shouting. What changed in March? Are we seeing more objects? Are we detecting more of what was always there? Or is there something about Earth's current position in space, something about where we happen to be in our orbit right now, that is relevant? The answer to that question takes you somewhere genuinely extraordinary. And it involves an object from outside our solar system that passed through our neighborhood just a few months ago, leaving behind something we still cannot fully characterize. Part 5, when random stops feeling random. Statistics is the science of separating signal from noise, and it is also frequently the science of resisting your own desperate desire to see a pattern. Human brains are pattern recognition machines. We evolved to find the tiger in the rustling grass, to connect cause with effect, to build narratives from data points. This is enormously useful for survival. It is also, in a scientific context, a constant source of potential error. So let's be honest about the observational bias problem before we go any further, because it is real and it matters. More people carry smartphones now than at any previous point in history. More homes have doorbell cameras and security systems. More cars have dash cams. The number of all-sky monitoring cameras operated by amateur and professional astronomers has grown significantly over the past decade. More sensors mean more detections. More detections mean more reports. More reports mean it feels like more is happening even if the underlying rate of events hasn't changed at all. This is a genuine confounding factor, and dismissing it would be intellectually dishonest. And yet the observational bias explanation only gets you so far before the physical characteristics of these specific events start to resist easy dismissal. The problem isn't just that people saw fireballs. It is that multiple events in this cluster were energetic enough to produce sonic booms. Sonic booms aren't a matter of perception or camera sensitivity. They're a physical effect of overpressure propagation through the atmosphere. You cannot get a sonic boom from a dust grain. You cannot get meteorite-producing falls from a surge in doorbell camera ownership. The Germany event left fragments on a rooftop. That is not a reporting artifact. That is a rock. The probability stacking is what makes the statistical picture genuinely awkward. Any single event in the March 2026 cluster could be waved away as coincidence. 2 events maybe. But when you stack multiple high-energy events with sonic booms with recovered fragments distributed across both North America and Europe inside a 3-week window on top of an already anomalous February sighting, the probability of all of that occurring by pure chance inside a single calendar month starts to require a larger than comfortable number of coincidences. Researchers studying fireball databases, catalogs maintained by organizations like the American Meteor Society and the European Fireball Network, have baseline rates for significant events, energetic enough to produce sonic booms, energetic enough to drop meteorites, energetic enough to be visible in daylight. Each of those categories has a typical frequency. March 2026 appears to exceed several of those baselines simultaneously. Not wildly. This isn't a once-in-a-century anomaly, but enough to register as statistically elevated when you look at the numbers dispassionately. The global distribution is also noteworthy. Meteor shower events cluster geographically and temporally. They come from a specific direction in the sky, so observers at certain latitudes see them better, and they peak at predictable times as Earth crosses a debris stream. The March events show no such pattern. Ohio and Louisiana and the Pacific Northwest and Germany and the northeastern United States are not consistent with a single directional source. They are spatially distributed in a way more consistent with Earth passing through a diffuse non-directional field of material than with any known meteor shower. The right scientific framing for this moment is not certainty. It is heightened curiosity. Something may be different about the density of material Earth is currently encountering in its orbit. That something could have several explanations, some mundane and some fascinating. The mundane explanation is statistical fluctuation plus observational bias. The fascinating explanation involves a source population that doesn't appear in any existing catalog. And here is where the hypothesis territory begins. Because when you ask where an unknown source population of small solar system objects might come from, when you ask what could have seeded Earth's orbital path with a temporary increase in debris, there is one candidate that keeps coming up in the conversations happening quietly among small-body astronomers. One object, one arrival, one departure, and a timeline that fits the March 2026 events with an alignment that is at minimum difficult to ignore. There is an object that passed through our solar system in the months before this cluster began. An interstellar visitor, only the third ever detected. It traveled along a trajectory almost perfectly aligned with Earth's orbital plane. It was extraordinarily active, releasing jets of gas and organic material, and it made its closest pass to Earth's orbit in December 2025, roughly 3 months before March. If it left a debris trail, you would expect that trail to intersect Earth's orbital path. And if that intersection happened in late winter and early spring of 2026, you would expect to see exactly what we are seeing now. The question is whether any of that is real, or whether we're doing exactly what human brains are built to do, finding the tiger in the grass when it might just be the wind. Part 6, the 3 Atlas alignment problem. In July 2025, a survey telescope in Hawaii called Atlas, the Asteroid Terrestrial Impact Last Alert System, spotted something moving across the sky. This happens constantly. Atlas is built for exactly this. But what the software flagged that night was not an asteroid. It was something moving too fast on a trajectory too unusual with an orbit that didn't close into an ellipse the way everything in our solar system does. The orbit was hyperbolic. The object was passing through, not orbiting. It had come from somewhere else. Designated 3 Atlas, the third interstellar object ever detected after Oumuamua in 2017 and Borisov in 2019. The visitor was immediately recognized as extraordinary, not just because of its origin, but because of its behavior. Oumuamua was strange and passive, a silent, elongated object that accelerated mysteriously and gave us almost nothing to analyze. Borisov was a fairly typical comet in terms of activity. 3 Atlas was something else entirely. It was the most active interstellar object ever observed. As it fell toward the sun and the heating intensified, it began erupting. Jets of gas and organic material blasted off its surface. Methanol, methane, carbon monoxide, water vapor. The activity levels were extraordinary, far beyond what you'd expect from its relatively modest size. Astronomers pointed every available telescope at it because this was a once-in-a-generation opportunity, a visitor from another star system close enough to study, active enough to be releasing its interior composition directly into space for analysis. The orbital characteristics of 3 Atlas are what make the March 2026 Fireball cluster relevant. Its trajectory brought it into the inner solar system along an orbit that was nearly coplanar with the ecliptic, the flat disk of space in which all the planets orbit the sun. This is geometrically significant. Most comets and asteroids approach the inner solar system at angles, crossing the ecliptic plane and moving away from it. 3 Atlas traveled almost within that plane. This means that anything it released along its trajectory, any debris, fragments, or larger chunks expelled by its jets, would tend to stay near the ecliptic, and Earth orbits within the ecliptic. The timeline is the piece that keeps demanding attention. 3I Atlas reached perihelion, its closest approach to the Sun, on October 30th, 2025. This is when solar heating was at its maximum, when jet activity was most intense, when the greatest volume of material was being expelled. Its closest approach to Earth's orbital distance came in December 2025 at roughly 1.8 astronomical units, about 167 million miles. Not close enough to be dangerous in any direct sense, but close enough that debris released near that point in its trajectory could potentially intersect Earth's orbit later. Then on March 16th, 2026, one day before the Ohio explosion, 3I Atlas made its closest approach to Jupiter. Jupiter's gravitational field is enormous. The flyby could have meaningfully altered the trajectories of any debris traveling in the object's general wake, potentially nudging material inward toward the Sun, toward Earth's orbital path. The convergence of dates here, perihelion in late October, closest Earth orbital approach in December, Jupiter flyby on March 16th, Ohio explosion on March 17th, is the kind of timeline that makes planetary scientists extremely uncomfortable because it sits in that ambiguous territory between suggestive and coincidental. No one has confirmed a debris link. No one has traced a fragment back to 3I Atlas with isotopic analysis. But the geometry, the trajectory, the activity level, the timing fit a debris trail hypothesis in a way that hasn't been publicly acknowledged to the degree the pattern arguably warrants. The question that follows naturally is deceptively simple. If 3I Atlas did leave large-scale debris along Earth's orbital path, where would those fragments go, and what would they look like when they arrived? Part 7, Debris Physics. Why some fragments would fall inward. When a comet or highly active small body releases material into space, which 3I Atlas was doing in extraordinary, almost unprecedented quantities during its solar approach, that material doesn't all receive the same memo about where to go next. The physics governing what happens to ejected debris depends almost entirely on one variable, the size of the particles involved. And the answer that variable produces creates a picture that is genuinely counterintuitive because our instincts about how things move in space are shaped by gravity. And gravity is not always the dominant force at play. Start with the smallest fraction, the dust grains, the submillimeter particles, the material that makes up the spectacular visual display we associate with active comets. When cometary jets release this material, it enters space with some initial velocity relative to the parent body and then immediately encounters a force that most people don't think of as physically significant: solar radiation pressure. The sun is not merely a source of light and heat. It is a source of physical pressure. Photons carry momentum, a consequence of quantum mechanics that seems almost paradoxical until you work through the mathematics. And when a stream of photons strikes a surface, it exerts a measurable force on that surface. For objects of normal size, this force is negligible compared to gravity. For objects small enough, specifically for particles where the ratio of surface area to mass becomes large enough, radiation pressure begins to compete with and eventually dominate over gravitational attraction. For submillimeter-sized particles, that threshold is crossed. Solar radiation pressure is stronger than solar gravity for tiny dust grains. And the result is that these particles get pushed outward away from the sun in the direction that the solar wind is blowing. This is, in a very literal sense, what a comet's tail is. When you look at a comet and see that glowing stream of material extending away from the sun, regardless of which direction the comet is traveling, you are watching solar radiation pressure at work, physically relocating the smallest ejecta into the outer solar system at speeds their own orbital dynamics would never produce. The dust goes out. It disperses. It becomes the diffuse background material of interplanetary space, contributing to the zodiacal light and eventually spreading too thin to be detectable as anything connected to its source. This is the fraction of 3I Atlas's ejecta that NASA's official dismissal of the debris hypothesis focuses on, correctly for that size range. Dust released by 3I Atlas near perihelion would be pushed outward by radiation pressure relatively quickly, dispersing away from the inner solar system rather than accumulating into an Earth-crossing hazard. If 3 Atlas released only dust, the debris trail hypothesis evaporates along with the dust. The physics doesn't support it. But 3I Atlas was not releasing only dust. It was erupting. The jet activity observed during its perihelion passage was extraordinary by any standard, outgassing at rates that surprised even researchers who had been tracking active comets for decades. And cometary jets, particularly violent ones from a geologically complex nucleus, do not release only submillimeter particles. They release a range of material from microscopic dust all the way up to centimeter scale, decimeter scale, and potentially meter scale fragments. Chunks of the nucleus itself loosened by thermal stress and mechanical disruption ejected into space with velocities that depend on the specific dynamics of each jet event. For this larger material, the centimeter to meter fraction, the physics is entirely different. At those sizes, the ratio of surface area to mass has decreased to the point where solar radiation pressure is no longer a significant force. Gravity dominates. And gravity in the complex dynamical environment of the inner solar system does not simply push things outward. It curves trajectories. It creates orbital families. It nudges objects along paths that can, over time scales ranging from weeks to years, bring them into intersection with the orbits of planets. Material released by 3 Atlas near its October 30th, 2025 perihelion would have been ejected into orbits that were broadly similar to the parent object's trajectory. Same general region of the inner solar system, same approximate ecliptic alignment, but not identical. Each fragment would have received a slightly different ejection velocity in a slightly different direction, producing a slightly different orbit. Over the weeks and months following perihelion, these orbits would evolve independently under the influence of solar gravity, Jupiter's gravitational perturbations, and the accumulated effect of every small force acting on each fragment. Some would decay inward, some would shift outward, some would evolve in ways that bring them across Earth's orbital path. The timeline is the element of this scenario that demands the most careful attention because it is either the most compelling coincidence in the story or its most important piece of supporting evidence, depending on which hypothesis you favor. Material released during the October 30th, 2025 perihelion passage, evolving under inner solar system dynamics for approximately 4 to 5 months, arrives at a window of potential Earth-crossing trajectories centered on late February and March 2026. That calculation is not precise modeling. It is an order of magnitude estimate based on the known geometry of 3I Atlas's trajectory and the general behavior of debris released near perihelion from objects in similar orbital configurations. The actual calculation would require detailed knowledge of ejection velocities, particle size distributions, and the specific three-dimensional geometry of 3I Atlas's path relative to Earth's orbit. That level of modeling has not appeared in publicly available literature, but the order of magnitude estimate aligns. Late October perihelion, 4 to 5 months of orbital evolution, late February to March arrival at potential Earth-crossing trajectories. The cluster of unusual fireball events begins in mid-February and peaks in mid-March. The timeline does not prove the hypothesis. It does not rule out coincidence. What it does is place the hypothesis in the category of things that cannot be dismissed on temporal ground alone, which is a higher bar than it might initially seem, because many speculative hypotheses fail immediately on timeline arguments. The concept that matters most for understanding what a 3 Atlas debris scenario would actually look like is intersection. Earth's orbit is a fixed ellipse around the Sun, a path that Earth follows with extraordinary precision, crossing the same points in space at the same times each year. If 3 Atlas traveled near the ecliptic plane and released larger fragments along its trajectory, those fragments, the gravity-dominated fraction that radiation pressure cannot simply blow away, would tend to remain near the ecliptic, near the region of space that Earth's orbit also occupies. Earth moving along its annual path at roughly 67,000 miles per hour would sweep through whatever was distributed in that region the way a windshield sweeps through rain. Most of it would be too small to matter. Dust and submillimeter particles that somehow survived radiation pressure dispersal would produce nothing noticeable. But the occasional larger chunk, centimeter scale, decimeter scale, meter scale, would interact with the atmosphere in ways that are very noticeable indeed. The crucial distinction between this scenario and a meteor shower is the one that keeps the hypothesis from being immediately testable against the fireball catalog. Meteor showers have structure. They have radiant points. They have predictable timing and predictable directionality because they come from coherent debris streams distributed along a parent comet's well-defined orbital path. Debris released by 3I Atlas would have none of those organizing properties. It would be diffuse, spread over a relatively short arc of the object's trajectory rather than distributed around an entire closed orbit. It would lack directional coherence because the ejection events that produced it were numerous, variable in direction, and distributed across a range of positions along the trajectory. Earth passing through it would not produce a shower. It would produce what looks like a temporary, modest, non-directional elevation in the background rate of sporadic fireball events. Indistinguishable in any individual event from the normal sporadic background, potentially distinguishable in aggregate only by the statistical elevation of the rate across multiple events in a compressed time window, which is with uncomfortable precision exactly what March 2026 looks like. The intellectual honesty requirement here is absolute, and it points in both directions. The physics of the hypothesis is plausible, not speculative in the sense of violating known physics, but genuinely consistent with how debris from an active body near the ecliptic would behave over a 4 to 5 month evolution period. The timeline is suggestive, not proven, not coincidental enough to dismiss, sitting in that uncomfortable middle ground where the honest answer is we don't know. The distribution of events is consistent, non-directional, temporally compressed, energetically elevated above recent baselines in ways that fit a diffuse debris field better than they fit a known shower. But consistent with is not confirmed by. This distinction is not a rhetorical escape hatch. It is the actual epistemic status of the hypothesis as of this telling, and collapsing it into either definitely connected or definitely not connected would be dishonest in either direction. What can be said with genuine confidence is that the hypothesis has not been ruled out by any publicly available data or analysis. And what makes it harder to dismiss than a simple coincidence is this. If you wanted to design a scenario that would produce exactly the March 2026 fireball pattern, sporadic, energetic, non-directional, temporally clustered, distributed across multiple continents, a diffuse debris field from an extraordinarily active interstellar object that passed near the ecliptic 4 to 5 months earlier is precisely what you would design. The prediction and the observation match. That is not proof. But in science, a hypothesis that correctly predicts the shape of the data before the data is examined occupies a different category than one assembled afterward to explain what was already known. And that difference is worth sitting with quietly while we wait for a laboratory in Germany to finish reading the autobiography of a rock. Part 8. Why these aren't meteor shower objects. Every year, with the reliability of a scheduled appointment, Earth passes through the debris trails left behind by known comets, and the sky responds with displays that human beings have been watching and cataloging for centuries. The Perseid meteor shower peaks around August 12th every single year. Not approximately, not roughly, but with a precision that reflects the clockwork geometry of orbital mechanics. The Leonids arrive in mid-November. The Geminids, arguably the most visually spectacular annual shower, producing more meteors per hour at peak than almost any other, light up the December sky with a consistency that amateur astronomers rely on the way farmers rely on seasons. You can plan around these events. You can book a campsite, drive away from city lights, lay out a sleeping bag, and watch the show with reasonable confidence that the show will occur because Earth has been crossing the same debris streams at the same points in its orbit for thousands of years, and the physics governing the crossing does not negotiate. The reason for this reliability is worth understanding because it is the foundation against which the March 2026 fireball cluster looks so anomalous. Meteor showers originate from comets. As a comet makes repeated passages through the inner solar system, solar heating causes it to shed material, dust, ice, small rocky fragments, along its orbital path. Over many orbits and many centuries, this ejected material spreads along the comet's trajectory, forming a diffuse stream of debris distributed through a tube of space that the comet traces on every circuit around the Sun. Earth's orbit intersects some of these tubes at specific fixed points. Every year, when Earth reaches one of those intersection points, it sweeps through the debris stream, and the particles that hit the atmosphere produce the meteors we see. The key feature of this process, the feature that makes it scientifically distinctive and immediately recognizable, is the radiant point. Because all the particles in a given debris stream are traveling on essentially parallel trajectories, the meteors they produce when they hit Earth's atmosphere appear to diverge from a single point in the sky. It is the same optical illusion that makes parallel train tracks appear to converge at a point on the horizon. Perspective geometry applied to meteors. The Perseids appear to radiate outward from the constellation Perseus. The Leonids appear to come from Leo. The Geminids emerge from Gemini. The radiant is the geometric fingerprint of a coherent debris stream, and it is the primary tool astronomers use to confirm that a given set of meteors belongs to a known shower rather than representing something else entirely. The radiant is also, in the context of March 2026, conspicuously absent. Go back through the fireball events of that month and look for a shared point of origin in the sky. The Ohio bolide, tracked across multiple states by dozens of independent cameras, came in on a trajectory inconsistent with any known March meteor shower. The Louisiana events, the Pacific Northwest sightings, the Germany fireball, their approach trajectories, where sufficient data exists to reconstruct them, point in different directions. There is no convergence. There is no Perseus or Leo or Gemini equivalent for March 2026. There is no location in the sky that you can point to and say everything came from there. The events are directionally incoherent with each other, which is exactly what you would not see if they were shower meteors, and exactly what you might see if they were something else. The only notable March meteor shower on the calendar is the Gametes, a minor event associated with a southern hemisphere radiant that produces no significant activity over North America or Europe under any circumstances. It is not a candidate explanation for fireball events over Ohio or Germany. Ruling it out takes approximately 30 seconds of checking the shower catalog. It has been ruled out. The energy argument reinforces the directional argument from a completely different angle. Meteor shower meteors are almost without exception composed of cometary dust. The fragile, low-density, loosely bound aggregates of silicate grains and organic material that comets shed as their ices sublimate under solar heating. These particles are structurally weak by the standards of solid rock. When they enter the atmosphere at high speed, the ram pressure tears them apart almost immediately at high altitude, producing a brief bright streak as their kinetic energy converts to light. They are spectacular to watch and essentially harmless in terms of ground-level effects. They disintegrate far above the weather layer, leaving no fragments, producing no sonic booms, delivering nothing to the surface. This is why meteor showers are beautiful rather than dangerous. The objects that produced the March 2026 fireball cluster did not behave this way. The Ohio bolide tracked across more than 30 miles of atmosphere before reaching its terminal fragmentation point, a journey that fragile cometary dust aggregates simply cannot survive. The ram pressure at atmospheric entry velocities would have destroyed a loosely bound dust aggregate within the first few miles of atmospheric contact. Something that covers 30 miles before exploding is something with structural integrity, something dense, something coherent enough to resist the forces that immediately destroy weaker material. That is the physical signature of a rocky body, an asteroid fragment, a chondrite, a piece of differentiated planetary material, not a remnant of a comet's dusty exhalation. The Germany event reinforces this point in the most direct way possible. It produced recovered meteorites, actual fragments of the original object, dense enough and structurally coherent enough to survive the full violence of atmospheric entry and reach the ground intact. You cannot recover meteorites from shower meteor. The material simply isn't there to recover. The Germany fragments are, by their mere existence on a rooftop in Koblenz Gulls, a statement about the physical nature of the object that produced them. This was rock, not dust, not ice, not the fragile debris of a comet's outer layers. Rock with the structural properties of a body that formed under significant heat and pressure, preserved its coherence through millions of years of travel through interplanetary space, and maintained enough integrity through atmospheric entry to deliver solid material to the surface. The fragmentation behavior of the March events, the specific way in which these objects broke apart, also looks different from the shower meteor profile in ways that specialists in bolide analysis find telling. Shower meteors characteristically flare. They brighten suddenly as aerodynamic pressure exceeds structural strength, fragmenting into many small pieces simultaneously, and then fade rapidly as the fragments decelerate and cool. The Ohio bolide followed a different pattern. It tracked as a coherent, brightening object for an extended period, suggesting it was resisting fragmentation rather than immediately succumbing to it. When it finally broke apart, it did so in what witnesses and instruments described as a single energetic terminal explosion. Not a gradual flare and fade, but an abrupt high-energy disintegration at depth in the atmosphere. That is the signature of a structurally coherent object that held together under mounting pressure until the stress finally exceeded its tensile strength all at once. Asteroid behavior, not comet dust behavior. The technical category that best fits the March events is sporadic meteoroids, the background population of rocky objects that Earth encounters continuously, arriving from all directions at varying speeds with no directional fingerprint and no predictable timing. Sporadics are asteroid fragments perturbed out of the main belt or other source regions by gravitational interactions over millions of years, scattered into Earth-crossing orbits through a slow, chaotic gravitational diffusion process that randomizes their approach directions over geological timescales. They're always present. Earth sweeps through them continuously. Most are small enough to disintegrate harmlessly at altitude. Occasionally one is large enough to produce an energetic air burst, a sonic boom, a meteorite fall. This happens. It is part of the normal operating background of Earth's interaction with the solar system. The question that March 2026 raises is not whether sporadics exist or whether they can produce fireball clusters by chance. They can, and they do. The question is whether the specific cluster of March 2026, its energy levels, its temporal compression, its continental distribution, its multiple sonic boom events, its recovered meteorite falls, is consistent with normal sporadic background variation, or whether it represents an elevated input from a source that isn't in the existing catalog. If the March events are normal sporadics, the asteroid belt explains them. No new physics, no interstellar connection, no revision of existing models required. If they represent an elevated input from an uncatalogued source, something that distributed material into apparently random Earth-crossing orbits in a compressed time frame, the asteroid belt explanation becomes strained, and the geometric coincidence of 3 Atlas becomes harder to dismiss as coincidence. What the evidence rules out is the comfortable, familiar, fully explainable scenario: a known shower, a known parent body, a known debris stream crossing a known point in Earth's orbit at a known time. All of that is ruled out by the absence of a radiant, the energy profile of the object, and the physical characteristics of the recovered material. What the evidence is consistent with is a range of possibilities that includes both mundane elevated sporadic activity and something considerably more interesting. The data needed to distinguish between those possibilities exists. It is being analyzed, and the scientific community's official position on all of this has been, depending on how you read it, either appropriately cautious or conspicuously quiet about the specific gaps in the public explanation. Because what scientists choose not to say in their official statements is sometimes exactly as informative as what they do. Part 9, the scientific pushback. NASA's public position on 3E Atlas is clear, consistent, and if you've been following this story, probably not surprising. Officials from the Planetary Defense Coordination Office have stated that the object poses no meaningful threat to Earth, that its trajectory does not significantly intersect with our orbital path, and that solar radiation pressure would rapidly disperse any particles it released long before they could reach us. The fireball events of March 2026, in NASA's official framing, are most likely attributable to normal variations in asteroid belt fragment migration. The ongoing, well-documented process by which rocks from the main belt between Mars and Jupiter are gravitationally nudged into Earth-crossing orbits over time. Bill Cook, who leads NASA's Meteoroid Environments Office and is one of the most experienced voices in the field, offered exactly this explanation in the days following the Ohio explosion. It is the same rational, parsimonious response that planetary defense scientists default to whenever fireball activity ticks upward. And it is worth understanding why. Because the reasoning is genuinely solid. The asteroid belt contains hundreds of millions of objects in a staggering range of sizes. Jupiter, the largest planet in the solar system with a gravitational influence that dwarfs everything else in the neighborhood, is constantly perturbing those objects, nudging their orbits, stirring the dynamics of the belt like a slow, immense gravitational mixing bowl that has been operating for 4.5 billion years. Fragments migrate inward continuously. Some of them, over time scales ranging from thousands to millions of years, end up in Earth-crossing orbits. The idea that a temporary cluster of impacts could emerge from this process by chance in any given month is not a stretch. It is in fact exactly what you would expect to happen occasionally in a solar system this busy. Occam's razor, the philosophical principle that the simplest explanation consistent with the evidence is usually the correct one, points cleanly toward the asteroid belt hypothesis. It requires no exotic source population. It invokes no unprecedented physics. It doesn't require 3E Atlas to have released the right particle sizes at the right ejection velocities at precisely the right points along its trajectory to produce a debris field that intersects Earth's orbital path months later. The asteroid belt explanation is what scientists call parsimonious. It explains the observations using mechanisms that are already known to exist and already known to operate in science. That counts for a great deal. So why are we still talking about 3E Atlas? Because the pushback against the interstellar debris hypothesis, the official scientific commentary that is filtered into the public domain, tends to focus almost exclusively on the small particle fraction of any potential debris release. Dust grains, pebbles, the submillimeter material that cometary jets are primarily known to produce. And for that size fraction, the dismissal is entirely justified. Solar radiation pressure acts on small particles quickly and powerfully, dispersing them outward away from the sun long before they could accumulate into any meaningful Earth-crossing population. If 3E Atlas released only dust, the debris hypothesis collapses immediately under straightforward physics. But here is the part of the conversation that has been notably quieter in the public scientific record. The behavior of larger fragments, material in the meter to decameter range, the size range that actually produces atmospheric fireballs, sonic booms, and meteorite falls, operates under completely different physics. At those sizes, solar radiation pressure is essentially irrelevant. The object's mass is too great for photon pressure to dominate its trajectory. Gravity takes over entirely, and the gravitational dynamics of meter-scale fragments released by an active body near perihelion are considerably more complex and considerably less thoroughly modeled in publicly available literature than the dust dynamics models of cometary debris dispersal. The published, peer-reviewed work that forms the scientific foundation for statements about what 3E Atlas did or didn't leave behind is overwhelmingly focused on the dust component. This makes sense from an observational standpoint. Dust is what forms the spectacular tails and comas that telescopes can actually image and analyze. Dust is what produces meteor showers. Dust is what the existing modeling infrastructure was built to characterize. The dynamical fate of larger ejecta, the chunks big enough to survive atmospheric entry intact and deliver meteorites to the ground, is frankly less thoroughly addressed in the open literature than the question deserves. This does not mean NASA is hiding something. That framing misunderstands how science works and how institutional scientific communication operates. What it means is that the specific question at the center of the March 2026 mystery: could 3E Atlas have released meter-scale fragments during its extraordinarily active perihelion passage? And if so, where would those fragments be now? May simply not have been rigorously answered in any publicly available analysis. The absence of a published model ruling out large fragment debris from 3E Atlas is not evidence that such debris exists. It is not a smoking gun, but it is a gap. And gaps in the scientific record are worth naming clearly rather than papering over with the most convenient available explanation. Science, despite how it is sometimes portrayed, is not a binary system where every question is either definitively proven or definitively disproven. It operates through degrees of confidence, through competing hypotheses held simultaneously at different probability weights, through the gradual and sometimes frustratingly slow accumulation of evidence that eventually tips the scales one way or the other. Right now, the asteroid belt explanation carries more weight, more prior probability, more parsimony, more institutional support. The 3E Atlas debris hypothesis carries less weight, more speculation, more geometric coincidence, more dependence on physical processes that haven't been modeled in sufficient detail. But less weight is not the same as ruled out. An honest science requires acknowledging that distinction. The honest scientific answer, the one that careful researchers will give you if you press them past the official talking points, is that the data needed to definitively distinguish between these two hypotheses hasn't been publicly released yet. And that data exists. It is sitting in a laboratory or waiting to get there in the form of meteorite fragments recovered from a rooftop and surrounding gardens in the Koblenz Gulls area of Germany following the March 8th fireball event. Isotopic analysis is the key that unlocks this question. Every piece of solid material in the solar system carries a chemical autobiography, a set of isotopic ratios that reflects the specific environment in which it formed, encoding information about the stellar neighborhood, the age of the material, and the processing history it has undergone. Material originating in the asteroid belt has well-characterized isotopic signatures built up from decades of meteorite analysis, spanning thousands of recovered samples from known fall events. Scientists know what asteroid belt material looks like at the isotopic level. They know the expected ratios of oxygen isotopes, chromium isotopes, titanium isotopes. They have a detailed fingerprint library. Material from an interstellar object, something that formed around a different star in a different part of the galaxy under different nucleosynthetic conditions in a molecular cloud with a different chemical history, would potentially carry isotopic ratios that don't match anything in that library. Not slightly different, potentially very different in ways that would be immediately apparent to an experienced meteoriticist looking at the mass spectrometry data. If the Germany fragments are analyzed and their isotopic composition fits neatly into the known asteroid belt catalog, the 3E Atlas hypothesis loses most of its remaining credibility. If those fragments show anomalous ratios, values outside the known range of solar system material, the conversation changes fundamentally. Not conclusively, not overnight, but the door opens wide. For now, the official position remains measured and reasonable, probably the asteroid belt. Monitor the Germany samples with interest. No cause for public alarm. That is not evasion. That is not institutional protectiveness or a coordinated suppression of inconvenient findings. That is good science doing exactly what good science is supposed to do, operating carefully under genuine uncertainty, refusing to leap to dramatic conclusions before the evidence supports them, and trusting that the process of analysis and peer review will eventually produce an answer worth having. The appropriate response to all of this for you sitting here listening is not fear. Fear is not a useful tool in this situation, and it is not what the evidence warrants. The appropriate response is curiosity patient, alert, genuinely engaged curiosity about a question that has real scientific stakes and a real answer waiting somewhere in a laboratory analysis that hasn't been published yet. Because here's the thing about the answer. Whenever it arrives, whether it confirms the mundane explanation or opens the door to something far more extraordinary, it will matter. It will matter for how we understand the debris environment of the inner solar system. It will matter for how we model the potential hazards posed by future interstellar visitors. It will matter in the broadest possible sense for our understanding of whether the material raining down on Earth in March 2026 came from our solar system's own ancient inventory or from somewhere else entirely. And right alongside this unresolved question, something else was happening in space that same week. Something entirely separate, entirely real, and arriving at an almost satirically inconvenient moment in the calendar. Something that had nothing to do with rocks or debris or interstellar visitors, and everything to do with the star at the center of our solar system, deciding that March 2026 was an excellent time to remind us who is really in charge. Part 10, the convergence window. 2 days after Ohio. That is how long it took for the next thing to arrive. On March 19th, 2026, NOAA's Space Weather Prediction Center issued a geomagnetic storm watch for Earth. The trigger was an active region on the sun's surface designated AR 4392, a magnetically complex, unstable patch of solar atmosphere that had been building tension for days, the way a fault line builds tension before an earthquake. It released that tension in the form of an M2.6 class solar flare. And the flare dragged something far more consequential behind it, a coronal mass ejection. An enormous, fast-moving cloud of magnetized plasma blasted off the sun's outer atmosphere and aimed, with the indifferent precision of orbital mechanics, directly at Earth. Speed estimates place the CME's arrival at roughly 72 hours after the flare, putting the moment of Earth impact squarely in the March 19th to 21 SD window, the same window, give or take a day, as the spring equinox. NOAA forecasters initially predicted a G2 geomagnetic storm with a meaningful possibility of escalation to G3 depending on a single critical variable, the orientation of the incoming plasma's magnetic field relative to Earth's own. If the two fields aligned in a specific unfavorable way, southward-pointing interplanetary magnetic field meeting Earth's northward-pointing field, the coupling efficiency increases dramatically and more energy pours into the magnetosphere than the baseline forecast accounts for. It is the difference between a glancing blow and a direct hit, and it is something forecasters cannot determine until the plasma is almost upon us. To calibrate what G2 and G3 actually mean in practical terms, it helps to look at the full scale. The NOAA geomagnetic storm scale runs from G1 minor to G5, which is the kind of event that rewrites history books. A G5 storm can collapse power grids across entire continents, disable satellites in low Earth orbit, corrupt GPS systems, and produce auroras visible from the tropics. The 1989 Quebec blackout, 9 hours without power for 6 million people in the middle of a Canadian winter, was caused by a geomagnetic storm. The Carrington event of 1859, the most powerful geomagnetic storm in recorded history, set telegraph wires on fire and produced auroras bright enough to read by in the Caribbean. That was a G5 by modern classification. A G2 to G3 storm is considerably more modest. High-frequency radio communications experience degradation, particularly at high latitudes. Satellites in certain orbits can experience increased atmospheric drag as the upper atmosphere expands slightly under the energy input. Power grid operators at high latitudes, Canada, Scandinavia, northern Russia, implement precautionary measures to protect transformers from voltage fluctuations. Auroras become visible at mid-latitudes, potentially as far south as the northern United States and Central Europe on a clear night. For most people, the experience of a G2 storm is nothing noticeable whatsoever and a possible light show in the northern sky if they happen to look up at the right moment. Not civilization ending, but not nothing either. Now here is where the timing introduces something that is, and this word is chosen carefully, genuinely interesting. March 19th fell 2 days before the spring equinox of 2026. And the spring equinox is not just an astronomical calendar marker. It has a specific, documented physical significance for how Earth responds to incoming space weather. The phenomenon is called the Russell-McFerrin effect, named after the two researchers who identified and characterized it in the 1973 paper that first described the mechanism. It is not controversial. It is not speculative. It is textbook space weather physics. Here's how it works. Earth's magnetic field, the magnetosphere, is generated by the churning motion of liquid iron in the planet's outer core. It is tilted relative to Earth's rotational axis, and that tilt has a specific geometric relationship with the plane of the solar system. At the equinoxes, twice a year, that geometric relationship reaches a configuration where Earth's magnetic field is optimally oriented to couple with the interplanetary magnetic field carried by the solar wind. Coupling in this context means energy transfer, the process by which the sun's magnetic field connects with Earth's magnetic field and allows solar wind particles to pour energy into the magnetosphere. More coupling equals more energy input equals stronger geomagnetic response to any given incoming disturbance. Put in the plainest possible terms, the equinoxes are the two moments each year when Earth's magnetic shielding is, by pure geometric accident, operating at its annual minimum effectiveness. A coronal mass ejection that arrives at the equinox hits harder, produces a stronger storm, transfers more energy, drives more intense auroras, and more significant technological disruption than the identical CME arriving in, say, July or December. The calendar, in this sense, is a vulnerability schedule, and March 19th to 21st sits right at the peak of spring vulnerability. The incoming CME of March 2026 was by itself not an extraordinary event. M-class flares and their associated CMEs are fairly common during periods of elevated solar activity, and the Sun in 2026 was operating near the peak of solar cycle 25, one of the more active cycles in recent memory. CMEs hit Earth regularly. Most of them produce minor to moderate geomagnetic responses and are forgotten within a news cycle. What made this one narratively significant was not its intrinsic power, but its timing, arriving into a magnetosphere already at its geometrically weakest point of the year, 2 days after a 7-ton asteroid exploded over Ohio in a month already defined by an unusual cluster of fireball events across 2 continents. Now let's be precise about something important, because this is exactly where a story like this can veer from fascinating into misleading. Intellectual honesty requires drawing a clear line. Coronal mass ejections do not cause meteors. They cannot. They do not attract asteroids. They do not seed the atmosphere with incoming rocks. They do not interact with the fireball population in any causal way whatsoever. A CME is a cloud of magnetized plasma, charged particles, and magnetic fields moving at millions of miles through interplanetary space. Fireballs are solid rocky objects following gravitational trajectories. These are entirely separate physical systems with no meaningful causal connection. Saying a CME caused the Ohio fireball would be like saying a thunderstorm caused your car to have a flat tire, because they happen on the same day. The reason the convergence of March 2026 is striking has nothing to do with physical causation. It has everything to do with timing and with a very specific, very human cognitive phenomenon that researchers have called narrative gravity. This is the tendency of the mind, when confronted with multiple independent signals converging simultaneously, to pull those signals into a single unified story. The brain is a pattern completion engine. It was built over millions of years of evolution to find connections, to see the tiger in the grass, to link cause with effect, to construct narratives from data. When multiple unusual things happen at the same time, the brain doesn't experience them as independent coincidences. It experiences them as chapters in the same story. Sometimes narrative gravity leads us to real insight. The history of science is full of cases where the intuition that two seemingly unrelated phenomena were actually connected turned out to be correct, where following the narrative led to a genuine discovery. Sometimes narrative gravity leads us astray, produces conspiracy theories, false patterns, connections that feel real because they feel real rather than because they are real. The convergence of March 2026 is right now in that ambiguous territory. Real in the sense that these events are all genuinely happening. Unproven in the sense that the causal web connecting them, if one exists, has not been established. What is established with complete certainty is something larger and more important than any individual event in this story. Earth is not a static object sitting in an empty, stable, unchanging void. It is a dynamic, constantly moving participant in an extraordinarily active cosmic environment. Geomagnetic storms are not rare catastrophes. They are scheduled events arriving at predictable intervals governed by the Sun's 11-year activity cycle. Asteroid impacts are not rare catastrophes. They are routine interactions between Earth and the debris-rich environment of the inner solar system occurring constantly at various scales. Interstellar visitors are not unprecedented impossibilities. We have now detected 3 of them in less than a decade. These are the normal operating conditions of a living planet in an active solar system. What is unusual about March 2026 is not that any one of these things happened. It is that several of them happened at once, loudly enough and closely enough together that even a distracted, news-saturated public noticed. Whether that simultaneity means something scientifically, whether there is a thread connecting the fireballs, the interstellar visitor, the solar storm, and the equinox into a single coherent picture, is the question this moment is asking. And the answer, whatever it turns out to be, begins with something already orbiting in the darkness of the outer solar system. Something new. Something that, when it comes fully online, will change what we are capable of seeing and force us to confront clearly and without evasion just how much of the sky we have been flying blind through all along. Part 11. The Vera Rubin Observatory just came online. For as long as humanity has been watching the sky professionally, with instruments, with intent, with the specific goal of cataloging what is up there, we have been operating under a constraint so fundamental that it shapes everything else. We can only watch a fraction of the sky at any given time, not because of laziness or insufficient funding or lack of ambition, but because of simple geometry. Telescopes are pointed instruments. They see what they are aimed at, nothing else. Every night survey teams around the world make choices. This patch of sky tonight, that patch tomorrow, and everything outside the current field of view goes unwatched. For most of human history, that was fine. The things we most needed to find were large enough, bright enough, and slow-moving enough that our narrow, sweeping surveys could catch them eventually. March 17th, 2026 demonstrated with considerable force what falls through the gaps. The Vera Rubin Observatory, sitting in the Atacama Desert of Chile at an altitude of nearly 9,000 feet above sea level, is the most ambitious attempt in the history of astronomy to close those gaps. Everything about it is built for scale. Its primary mirror spans 8.4 meters, large enough to collect extraordinary amounts of light from faint, distant objects. Its camera, formerly called the Legacy Survey of Space and Time Camera, or LSSD, is 320 megapixels, the largest digital camera ever constructed for astronomical use. To put that in perspective, a typical high-end professional camera shoots around 45 to 60 megapixels. The LSSD camera is roughly 6 times that. Designed to capture an area of sky about 40 times the size of the full moon in a single exposure. Every night, without interruption, Rubin will image the entire visible sky multiple times, building a continuous time-lapse record of everything that moves, flickers, brightens, or appears where nothing was before. The numbers describing what Rubin is expected to find border on the overwhelming. Current asteroid catalogs, the cumulative result of decades of survey work by every telescope ever pointed at the problem, contain roughly 1 million known objects. Rubin is projected to detect 5 to 10 million new asteroids within its first few years of full operation. Among those will be hundreds of thousands of previously unknown near-Earth objects, rocks whose orbits bring them into Earth's neighborhood, the population from which impactors like the Ohio bolide originate. Objects that are currently invisible, too faint for existing surveys to register at typical detection distances, will suddenly have names and orbital parameters and risk assessments. The catalog of known potential hazards is about to expand by an order of magnitude. For planetary defense, this is genuinely transformative. The more objects we know about, the more lead time we have for the ones that matter. An asteroid discovered 10 years before a potential impact gives civilization options that an asteroid discovered 10 hours before impact simply does not. Rubin's contribution to the warning timeline, the gap between we found it and it arrives, will be measured in years for thousands of objects that currently don't even have names. But here's the thing that needs to be said clearly, because the temptation to read the Rubin story as a solution rather than an improvement is strong and understandable and wrong. Vera Rubin does not solve the Ohio problem. Events like March 17th, 2026 will happen again after Rubin is fully operational. The fundamental physical constraints that made the Ohio impactor invisible until it arrived have not been engineered away. They have been reduced in some size ranges for some approach geometries. They have not been eliminated. The first constraint is what astronomers call the cadence problem. Rubin surveys the entire sky every few nights, an extraordinary achievement, but still a finite interval. An object that enters Earth's vicinity between re-observations of a given sky patch can still go completely undetected until it hits the atmosphere. For objects in the 1 to 5 meter size range, the range that produced the Ohio explosion, even Rubin's exceptional sensitivity may be insufficient to detect them at the distances where meaningful warning time begins. These objects are small, dark, and fast. At typical astrodetection distances, they produce a signal so faint that it sits below the detection threshold until the object is close enough that warning time is measured in hours rather than days. Hours is not enough time to evacuate a city. Hours is barely enough time to issue a public alert. The second constraint is geometric and essentially permanent for any ground-based system. No telescope on Earth's surface can observe the daytime sky. The sun's glare renders the entire sunward hemisphere of the sky invisible to optical astronomy during daylight hours. Objects approaching Earth from the direction of the sun, which, due to the geometry of intersolar system orbits, is an extremely common approach direction for Earth-crossing asteroids, remain hidden in solar glare until they cross into the night side of the sky. By the time they are observable, they are often already inside Earth's minimum safe response time. The Ohio impactor almost certainly came from a sunward direction, consistent with its morning arrival. Rubin, for all its magnificence, cannot see through the sun any more than your eyes can. Solving the sunward approach problem requires getting off the ground entirely. A space-based observatory positioned at a different point in the solar system, ideally in an orbit that keeps it between Earth and the sun or displaced to one side of the Earth-Sun line, could watch the sunward sky continuously, detecting objects that are permanently invisible from Earth's surface. NASA's proposed NEO Surveyor mission is designed precisely for this purpose. An infrared space telescope optimized for asteroid detection positioned to cover the approach directions that ground-based surveys structurally cannot reach. Whether and when NEO Surveyor gets the funding and timeline it needs to actually launch and operate is a question whose answer carries real consequences for how many future Ohio-class events arrive without warning. The philosophical dimension of Rubin's arrival is in some ways the most significant thing about it. More significant in the long arc of history than any specific asteroid it will or won't detect. For the first time in the 4-billion-year history of life on this planet, a species living on Earth has built a tool specifically designed for continuous, systematic surveillance of the entire sky. Not for navigation, not for religion or calendar making, not for the scientific study of any particular class of object, for watching, for the explicit purpose of knowing as comprehensively as possible what is out there and where it is going. Every previous civilization that existed on this planet lived and died under a sky it could not monitor. Dinosaurs had no warning of the Chicxulub impactor. The people of the Tunguska region of Siberia in 1908 had no warning of the explosion that flattened 2,000 square kilometers of forest. The residents of Chelyabinsk in 2013 had no warning of the shockwave that injured over 1,000 people and shattered windows across the city. The commuters and residents of Medina County, Ohio, on March 17, 2026 had no warning of the detonation that shook their homes and flooded their emergency services. In every one of those cases, the first warning was the event itself. Rubin represents the first serious systematic attempt to change that relationship, to move humanity from reactive to anticipatory, from surprise to watching. That is not a small thing. That is arguably one of the most consequential shifts in our species' relationship with its cosmic environment since we first looked up and started asking questions about what we saw. And yet the question that March 2026 made newly urgent is not simply what is out there. Any honest assessment of where we stand has to sit with a harder version of the question. What might already be close right now that we still cannot see? Rubin expands the catalog enormously. It does not make the catalog complete. The Ohio impactor would almost certainly not have been detected by Rubin in time to provide actionable warning. The sunward approach, the small size, the speed, all of those factors persist as blind spots. Even in a Rubin-era sky survey, detection is necessary but not sufficient. The other half of the equation, arguably the half that matters more once you have found something, is response. What do you do with a warning when you have it? What does a 24-hour warning of an Ohio-class impactor actually enable? What does a 1-hour warning enable? What does a 10-year warning enable? These questions have different answers, and the answers depend not just on technology, but on political will, international coordination, and the unglamorous work of building planetary defense infrastructure before it is needed rather than after. March 2026 handed us a loud, vivid, impossible to ignore demonstration of what the absence of warning looks like. What we do with that demonstration, whether it accelerates the timeline on NEO Surveyor, whether it generates the political momentum to fund the response infrastructure that detection alone cannot provide, is the chapter of this story that hasn't been written yet. And the next part of the story takes us somewhere perhaps even more disquieting, to a piece of physical evidence already on the ground, already in someone's hands that may hold the answer to the deepest question March 2026 raised. Part 12. Europe's March 8th impact. The quiet confirmation. While the Ohio explosion dominated the headlines in North America, the flooded 911 lines, the shaking buildings, the meteorite hunters fanning out across Medina County with metal detectors and a gleam in their eyes, the event that may ultimately prove to be the most scientifically significant thing that happened in March 2026 unfolded quietly over Central Europe on the 8th, 9 days earlier. Witnessed by millions of people across an entire continent and discussed outside the planetary science community almost not at all. The European Space Agency confirmed a major fireball event observed simultaneously across multiple countries on the night of March 8th. The reports came in from Germany, France, Belgium, the Netherlands, and several neighboring nations, all describing the same object, the same trajectory, the same terminal flash. Security cameras, doorbell systems, dash cams, and dedicated all-sky astronomy networks captured it from dozens of independent angles. The ESA's confirmation was based on triangulated data from multiple observation networks, cross-referenced with infrasound detections and eyewitness reports spanning hundreds of kilometers. This was not a regional anomaly or a misidentified aircraft. This was a confirmed, well-documented, energetic atmospheric entry over one of the most densely instrumented and densely populated regions on Earth. The luminous trajectory lasted approximately 6 seconds. That number requires a moment of appreciation because 6 seconds is a long time for a fireball. Most atmospheric entries in the fireball category, bright enough to exceed Venus in peak luminosity, last between 1 and 3 seconds from first appearance to terminal fragmentation. 1 to 3 seconds is the window in which a rocky object plunges through the upper atmosphere, compresses the air ahead of it into plasma, and either disintegrates completely or survives to deliver fragments to the ground. 6 seconds is nearly double the upper end of that typical range. What 6 seconds tells you about the object is specific and informative. It was large enough to maintain structural integrity through the upper atmospheric entry phase. It was dense enough to resist the ram pressure, the crushing force of compressed air that destroys fragile, low-density objects almost immediately upon atmospheric contact. And it was traveling at a trajectory angle shallow enough to extend its atmospheric path, moving more horizontally than vertically, covering more ground before the pressure became too great. Shallow entry angles produce longer, more spectacular trajectories and, critically, give the object more time to decelerate before the final fragmentation, which increases the probability of surface-reaching fragments surviving the journey. The sonic boom arrived minutes after the visual event, as it always does. Sound traveling at its leisurely pace behind the instantaneous light of the plasma trail. Observers who had already gone back inside, convinced the spectacle was over, found their windows rattling and their walls shaking from a source that seemed to come from everywhere at once. Several people in Germany reported the boom as the most startling part of the experience, more viscerally alarming than the light, because by then they had lowered their guard. And then in the days that followed came the discovery that elevated this event from spectacular to scientifically extraordinary. Meteorite fragments were recovered in the Koblenz-Gulz area of western Germany. Not one fragment. Multiple pieces distributed across a residential area in the pattern characteristic of fragmentation-strewn field. A homeowner discovered material on their roof. Additional pieces turned up in gardens, in fields, and on hard surfaces in the surrounding neighborhood with a contrast against pavement or soil made them findable. The fragments were dark, dense, and clearly foreign to the local geology. The unmistakable profile of material that had arrived from somewhere other than Earth. Recovered meteorite material is far rarer than the frequency of fireball events would suggest. The vast majority of objects that produce visible fireballs, even energetic ones, never reach the ground as recoverable material. They are fragile, porous, low-density aggregates of dust and ice and loosely bound silicates held together more by habit than by structural strength. The violence of atmospheric entry tears them apart at altitude, converting their mass into light, heat, and shockwave energy, leaving nothing behind but a brief disturbance in the sky and a sonic boom that fades into the background noise of human civilization within hours. Objects that survive as meteorites are different in kind. They are structurally coherent, dense, tough, mechanically resistant to the forces that destroy their more fragile counterparts. The meteorite catalog that scientists have built over centuries of collection and analysis is dominated by 3 broad types. Stony meteorites, which are the most common and include the chondrites that preserve some of the oldest material in the solar system. Stony iron meteorites, which represent boundary material from the cores and mantles of differentiated parent bodies, and iron meteorites, which are the remnant cores of planets that formed differentiated and were subsequently shattered by collisions billions of years ago. Each type has a physical profile that reflects its origin and history. The Germany fragments, by virtue of surviving atmospheric entry intact, already tell us something. Whatever produced them was not a dust aggregate from a cometary tail. It was rock, coherent, dense, structurally capable rock. The scientific value of recovered meteorite material cannot be overstated, and it goes far beyond the novelty of having a piece of space in your hand. A meteorite is a time capsule. Its mineralogy records the conditions under which it formed, the temperature, pressure, and chemical environment of its parent body's surface or interior. Its isotopic composition records something deeper still, the nuclear history of the material itself, encoding information that stretches back to the stellar environments where the atoms were forged. When meteoriticists talk about isotopic analysis, they are talking about reading a document written in the language of nuclear physics, a document whose authorship is the history of the universe. Every meteorite type in the existing catalog has a characteristic isotopic fingerprint, a specific set of ratios among isotopes of oxygen, chromium, titanium, and other elements that places it unambiguously within the family of known solar system material. Ordinary chondrites cluster around a specific oxygen isotopic composition. Carbonaceous chondrites occupy a different region of the same isotopic space. Iron meteorites, instatite chondrites, lunar meteorites, Martian meteorites, each has its address in the multidimensional space of isotopic ratios. And that address was established by the solar nebula from which our entire solar system condensed 4.5 billion years ago. All of it, every meteorite ever analyzed from every fall in the historical record, traces back to the same original cloud of gas and dust orbiting the same young star. Material from outside that system would not have that address. It would carry the isotopic signature of a different stellar environment, a different nucleosynthetic history, different ratios of elements produced by different generations of stellar evolution in a different part of the galaxy. It would stand out in the isotopic catalog the way a sentence in a foreign language stands out in a page of familiar text, immediately recognizable as different, requiring explanation. The researchers who are currently, presumably, analyzing the Germany fragments know all of this. They are also acutely aware of the weight that any unusual result would carry and the scrutiny it would attract. The scientific community's experience with extraordinary claims about interstellar material has been, in recent years, instructive. The controversy surrounding claims of interstellar meteorite material recovered from the seafloor, involving spherules analyzed by researchers who argued they showed anomalous isotopic compositions consistent with an extrasolar origin, generated enormous attention and equally enormous skepticism. The institutional memory of that episode is fresh. Nobody working on the Germany samples wants to announce interstellar material and then spend the next 5 years defending a result that doesn't hold up to replication. The caution is rational. The bar for an extraordinary claim is appropriately high, which means the results, when they come, will have been checked and rechecked. The analysis pipeline for something this consequential involves multiple independent laboratories, multiple isotopic systems, multiple cross-validation steps. It takes time, months, possibly longer, for a result this significant to reach a form that the authors are willing to submit for peer review and that peer reviewers are willing to pass. The absence of published results as of this telling is not suspicious. It is simply the pace of careful science applied to a question that matters enormously. But here is what makes the waiting genuinely compelling rather than merely frustrating. Somewhere in Germany right now, on a laboratory bench in a clean room inside a mass spectrometer performing the patient precise work of counting isotopes one atom at a time, there's a small piece of rock. Maybe the size of a golf ball, maybe the size of a fist, dark and utterly indifferent to the significance humans have attached to it. It does not know that an entire hypothesis about an interstellar visitor hangs on its chemistry. It does not know that its isotopic ratios could either confirm the mundane explanation for March 2026's unusual sky or blow the entire story open in a direction that nobody is fully prepared for. The whole edifice of speculation and hypothesis and careful scientific hedging that this story has built could stand or fall on what that fragment contains. And the answer, when it comes, will arrive not with a bang, but with a number, a ratio printed in a table in a journal paper that most people will never read, describing something that may turn out to be the most important small piece of rock ever to land on a German rooftop. Part 13. The rise of AI-driven sky monitoring. Something changed in the years before March 2026 that had nothing to do with telescopes or government space agencies or planetary defense budgets. It didn't happen at a conference or in a research paper or as the result of any coordinated scientific initiative. It happened quietly, incrementally, driven almost entirely by consumer behavior and commercial incentives that had nothing whatsoever to do with watching the sky. And it may turn out to be one of the most consequential developments in the history of planetary monitoring. Not because anyone planned it that way, but precisely because nobody did. The entire surface of the developed world became covered in cameras. Not astronomy cameras, not purpose-built sky survey instruments pointed at carefully chosen patches of darkness. Ordinary cameras, the kind attached to doorbells because a homeowner was worried about package theft. The kind mounted on dashboards because an insurance company offered a discount. The kind embedded in parking lot security systems, watching empty asphalt at 3 in the morning. The kind carried in every pocket on every street in every city, ready to record anything unusual at a moment's notice. Each one watching its tiny slice of the world for reasons that had nothing to do with space rocks, and collectively, accidentally, creating something that planetary scientists could only have dreamed of a generation ago. The Fireball Detection Network that documented the March 2026 events was not built. It assembled itself. It grew organically from millions of independent decisions by millions of unconnected people, each adding one more camera to one more corner of one more patch of sky until the cumulative coverage reached a density that functions in practice like a continuous observational grid spanning entire continents. When the Ohio Fireball crossed the sky at 8:57 a.m. on March 17th, it was captured on dozens of independent cameras within the first few minutes. Doorbell cameras in suburban Cleveland, dash cams on Interstate 77, security systems outside warehouses and schools and office buildings across northeastern Ohio and western Pennsylvania. A retired amateur astronomer's all-sky camera running continuously in his backyard outside Akron, recording a hemisphere of sky every 30 seconds, discovered the footage only after his neighbor texted him asking if he had felt the boom. The triangulation of the Ohio Fireball's trajectory, the precise calculation of where it came from, what angle it entered the atmosphere, where it was headed, and where fragments most likely fell, was accomplished in part using footage from systems whose owners had no idea they were participating in planetary science. The mathematics of trajectory reconstruction requires multiple observations from different geographic positions, each providing a slightly different viewing angle on the same event. The accidental camera network provided exactly that, with a density of independent viewpoints that dedicated fireball monitoring networks couldn't have matched even with significant additional funding. This is new. It is genuinely historically new. 20 years ago, a fireball over Ohio might have generated a handful of eyewitness reports, possibly one or two grainy photographs, and a seismic signature from nearby instruments. The trajectory would have been poorly constrained. The strewn field, the area where fragments fell, would have been a rough estimate covering hundreds of square kilometers. Meteorite hunters would have been working from guesswork as much as science. In 2026, the same event produced dozens of calibrated video records, precise trajectory calculations, a well-constrained strewn field, and a public documentation archive assembled within hours. The camera revolution did that. Not NASA, not a planetary defense initiative. A billion ordinary people buying security systems and dash cams for reasons that had nothing to do with asteroids. Artificial intelligence is now transforming what this distributed network is capable of, and the transformation is accelerating faster than most people realize. The bottleneck in fireball documentation has always been human review. A fireball event might generate footage from hundreds of cameras, but identifying which cameras captured something relevant, extracting the usable frames, and performing the geometric calculations required for the trajectory reconstruction traditionally required specialists working for hours or days. Machine learning systems trained on large data sets of known fireball events can now do most of that work automatically. They can scan incoming footage from camera networks, identify the distinctive optical signature of a fireball, the specific brightness profile, the angular motion, the terminal flash of fragmentation, and flag relevant footage for human review within minutes of an event occurring. They can extract trajectory information directly from video metadata. They can produce preliminary energy estimates based on light curve analysis. What once took a team of researchers days now takes an algorithm minutes. The integration of AI pattern recognition with satellite data streams is where the capability becomes genuinely extraordinary. The GOES 19 lightning mapper that detected the Ohio Fireball's plasma trail was not designed for meteor detection. It was built to track lightning, but the optical signature of a fireball plasma channel is similar enough to a lightning discharge that the instrument captures it. And that data stream, along with data from other weather and Earth observation satellites not designed for planetary science, can be fed into AI systems trained to recognize atmospheric impact signatures. The result is a detection layer that covers the entire Earth simultaneously from orbit at all times, regardless of cloud cover or time of day. A layer that's satellite detection capability over the ground-based camera network, and then add the infrasound detection system. The global array of extremely sensitive microphones originally deployed to monitor compliance with the Nuclear Test Ban Treaty, which detect the low-frequency pressure waves produced by large atmospheric explosions with extraordinary sensitivity and geographic precision. And you have something remarkable, a planetary detection system for atmospheric impacts assembled almost entirely from infrastructure built for other purposes that now covers the Earth with an observational completeness that no dedicated meteor monitoring network has ever achieved. The infrasound network deserves particular appreciation here because it is perhaps the most powerful and least celebrated component of the accidental detection infrastructure. The Comprehensive Nuclear Test Ban Treaty Organization operates 60 infrasound stations distributed around the globe, each consisting of arrays of microphones capable of detecting pressure waves at frequencies far below human hearing. These stations were built to catch clandestine nuclear tests. What they also catch, continuously and automatically, is every large atmospheric impact anywhere on Earth. Every bolide energetic enough to produce a significant shock wave regardless of whether it occurred over an ocean, a polar ice cap, a rainforest, or a populated area. The Ohio event registered on multiple infrasound stations simultaneously. The energy estimate derived from infrasound data was among the most reliable produced in the first hours after the impact, before any visual data had been fully analyzed. The honest accounting of all this capability, however, requires confronting the limitation that sits at the center of everything described so far. All of it, every camera, every satellite instrument, every infrasound microphone, every AI classifier running on every data stream, is reactive. It tells you an object has arrived. It does not tell you one is coming. The documentation gap, the time between an event occurring and humans having a detailed record of it, has been reduced by the accidental camera revolution and its AI amplification from days to minutes. That is a genuine and significant achievement. The warning gap is a different problem entirely, and it remains essentially unsolved for the size class of objects that produce the Ohio explosion. The warning gap is the time between detecting an incoming object and its arrival, the window in which theoretically some response could be mounted. For the Ohio impactor, that window was 0, not because detection systems failed, but because the object was never detected until it was already inside the atmosphere, at which point the warning gap had already closed. Dash cams and doorbells cannot look outward into space. AI classifiers running on security footage cannot see objects that haven't entered the atmosphere yet. The entire ground-based camera ecosystem, for all its extraordinary documentary power, contributes nothing to the warning problem. And this is where the philosophical weight of the moment becomes difficult to avoid. Consider what humanity has built, accidentally and without coordination, in the space of roughly 2 decades. A planetary nervous system, a continuous global multi-layered sensory apparatus that watches the sky from the ground and from orbit, processes what it sees with machine intelligence operating at speeds no human analyst can match, and produces a near real-time record of everything energetic enough to make itself known. For 4.5 billion years, this planet absorbed impacts in complete darkness. No record, no witness, no aftermath beyond the physical scar. Now, every significant atmospheric entry anywhere on Earth is documented within minutes, analyzed within hours, and archived permanently. That is not nothing. That is, in fact, extraordinary. A transformation in our relationship with our cosmic environment that happened so gradually and so distributed across so many unconnected decisions that most people have no idea it occurred. We built a planetary nervous system without meaning to. We should probably now build the thing it was always missing, the ability not just to feel the impact, but to see the blow coming. Because the question that March 2026 made impossible to defer any longer is not whether we can document what hits us. We have solved that more or less with doorbell cameras and treaty monitor microphones. The question is whether we can see it coming in time to do something about it. And if we could, what exactly that something would be. The answer to that question requires going somewhere no ground-based camera can reach. And it starts with being honest about how much of the sky we are still, right now, flying completely blind through. Part 14. A sun grazer is approaching. By the time Comet 2026-A1, designated maps by the team that first characterized its orbit, entered the conversation, most people following the March 2026 story had already reached their limit for cosmic coincidence. An interstellar visitor on a suspicious trajectory. A fireball cluster across 2 continents. A solar storm timed to the equinox. And now this. One more object, one more arrival, one more entry in what was becoming an almost satirically crowded inventory of things happening simultaneously in the inner solar system. Comet Maps is a sun grazer. That word sounds almost gentle, like something grazing in a field. It is not gentle. A sun grazer is a comet whose orbital path carries it into an extremely close approach with the sun, inside the orbit of Mercury, into a region of space where the physics of solar proximity stop being merely interesting and start being catastrophic. The sun at that distance is not the warm, distant light source you see from Earth. It is an overwhelming, all-consuming presence delivering energy at intensities that transform the behavior of any material unfortunate enough to find itself nearby. To understand what happens to a comet in that environment, start with what a comet is under normal circumstances. At typical distances from the sun, in the outer solar system, or even in the asteroid belt region, a cometary nucleus is a relatively stable object. It is a mixture of rock, dust, and various ices. Water ice, carbon dioxide ice, carbon monoxide ice, more exotic frozen compounds layered and compressed into a body that can range from a few hundred meters to tens of kilometers across. Solar heating at those distances is gentle enough that the comet releases material gradually, sublimating ice from its surface, producing jets of gas and dust that form the coma and tail that make comets visually spectacular from Earth. The nucleus itself remains structurally intact. It is cold, dark, and old, preserving material that in some cases dates back to the formation of the solar system itself. Now move that object inside Mercury's orbit. The solar flux, the energy delivered per unit area per unit time, increases as the inverse square of distance from the sun. Half the distance, quadruple the energy. At sun grazer perihelion distances, the energy input is not 4 times what Earth receives. It is tens to hundreds of times greater depending on the specific orbital parameters. Surface temperatures on a sun-grazing nucleus can reach levels sufficient to vaporize not just ice, but silicate rock. The outgassing that results is not the gentle sublimation of a normal comet passing through the inner solar system. It is violent, explosive, and deeply destabilizing to the structural integrity of the nucleus. Jets of gas and dust blast off the surface with velocities far exceeding those of a typical comet at normal distances. The thermal stress penetrates inward, fracturing material along pre-existing weaknesses in the nuclear structure. Tidal forces from the sun's gravity, the differential pull on the near side of the nucleus versus the far side, add mechanical stress on top of. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.